complex flow domains and how we best approach complex flow domains in ANSYS Fluent and the CFX. So I'll start off with a PowerPoint slide and describing the problem of interest and what we're looking at. So we know if you work with the CFD simulations and you know a flow domain is quite complex, and that's very often complex, because the flow will often passes through complex objects, like gaps, engineering clearances, seals, very highly curved surfaces. So as a result, and you have these flow passages, and which is very narrow, very thin, and very long, and with high curvature, and that needs to be resolved to get the good solution out of it. So starting with meshing. If we are given with such a task, to perform analysis on a complex flow geometry, starting with the meshing part, the most common approach is, how do I generate a mesh for a very complex domain? Obviously, I'm going to look for a probably the easiest method available for such a domain. Just go with the tetrahedron plus prism elements. Prism elements, if you attended our last seminar for inflation layers, that's to resolve the boundary layer in these sections attached to these surfaces. So this is probably the most common method used to mesh a complex flow domain, because it's probably the most robust, can handle complex geometry, and you have the advantage of using tetrahedrons. You can put tetrahedrons into very oddly shaped geometry and surfaces, right? And it's convenient. However, the mesh that you get, could be because of the isotropic nature of the tetrahedron elements, right? We're going to have a very large, sometimes excessive element count, because tetrahedrons are not easily stretched in one direction or another, and they have aspect ratio most likely stayed in 0.5, 0.6 range. So it's not easy to stretch the elements. If you want to use the elements, tetrahedron elements for thin gaps, you're going to resolve in you use many elements put into the thin gap to resolve that section. And the other issue could be like in the same flow domain, you have very disproportional element size ratio. From the elements in the thin gap could be on the order of microns, and then to the other flow domains, you have element size of millimeter or centimeter or an inch, and you have an element ratio of 1,000 to 1. This, because of the element count, the meshing could take a long time. The mesh could take a long time to generate, to fill these tight spacing and gaps and putting 10 million elements in those places. And sometimes the workbench, will fail to handle these problematic geometry. If you use workbench meshing enough and you handle some of these difficult situations, and you probably have seen those, run into difficult, problematic geometries. So with that in mind, and is there any other way, alternative approach for this kind of issues? So I'm going to bring up the problem of interest. I'm using a simple geometry to demonstrate what we're talking about today. I have a tight gap. It's not really tight, but it's a narrow gap, like a cylindrical shape, with attached on top of that, there's a flow volume. It's rectangular. But with the combination of those, the whole flow domain is a single part and it's not sweepable. Okay, if the inner surface is rotating at some RPM, for example, now I need to resolve the shears in the gap, in the flow gap. So for this case, I really can't use very large element count, large element, for the gaps, like 1 or 2 elements, because I'm not solving anything. I will be very likely to go to this type of meshing situations, okay? And with tetrahedrons plus prisms, and we end up with 1.26 billion elements. So at this point, I would like to show you what we have here. So this is the mesh that we talk about, right? You just seen. I have a single fluid part, and if in order to resolve the flow gap, I create some prism layers. That's the best I can do, plus the combination of tetrahedrons. I have roughly 7 or 8 elements across. I can get more, but that would triple or quadruple my element count easily. And because of the isotropic nature of tetrahedron elements, and you see in the axial direction, right? Because I can't really stretch tetrahedron easily. I end up using way more elements that I need, right? In the axial direction, you could see that. I don't need that many in the axial direction. I need more in the radial direction. So that's a case of interest. I mean, I could get a mesh out of this, but after I have the meshing method using the tetrahedron patch conforming meshing method with D4 inflation layers, I end up with 1.26 million elements. Right? This is just a simple case. If the gap right now is a 1/4 inch, I just set up to about 1/4 inch gap. If the gap becomes smaller and smaller, like in the current situation, we're looking at the 10 thou or 20 thou situation, then this element count will go up because the element size to fill in these gaps becomes smaller if you want to use tetrahedrons. And just to resolve that, I could be looking at 6-7 million elements for such a geometry. So that's probably not ideal. So what we're going to do about it? So next thing that we can do is, instead of using one part, okay, let's take some advantage. Okay, let's go back to PowerPoint for a moment here. Okay. So by looking at the features of a flow domain, we probably can find a way to split that into separate 3D volumes. And for each 3D volume, right, look for an available workbench meshing method. Probably find the best fit for each flow volume. Starting with, is this flow volume sweepable, or can I apply a multi-zone method? Both will give us, like a hex mesh or a hex dominant mesh with inflation layers, and which I could use, very efficiently, for different type of geometry. So based on your flow domain decomposition, I can cut out or slice off sections that is sweepable, or different methods I can apply. And by doing that, I can reduce the element count and reduce the overall CPU time, which is a direct result of the reduced element count, right? And once I have these flow parts, flow volumes meshed, then I can bring these volumes into either CFX or Fluent and sort of stitch them together. For example, I have 3 flow volumes. I can use the domain interface functions features in CFX or mesh interface in Fluent to put them together. Okay. Now let's go back to the demo to see what it's like. And now for our flow domain, I kind of separate them into 3 flow volumes. The first is the rectangular part on top of the cylinder, and I have a cutout and of the section underneath, and I have the majority of the gap in that section. So by separating the flow volume into 3 parts, and now what will be the into 3 flow volumes, but now I assign them. I form a multi-body part right here, as you can see here. Okay, this is a multi-body part in Workbench. Okay, what would the mesh look like? So by doing this, okay, now I'm no longer being restricted, to a non-sweepable body or volume. I can now take advantage of the Workbench meshing method to assign meshing method to each one. So by looking at this, all 3 parts are sweepable. So you see here, I assigned the sweep method for first one, and that's the sweep method for that one. And then because of these three flow volumes, they belong in the same multi-body part. And the top, the rectangular section, would be meshed based on whatever mesh is generated from here. And Workbench would generate a flow-through mesh across these interspaces, between these volumes. So what would the mesh look like? And to mesh this, of course, in addition to the method, I'd assign, like a sizing, the number of elements that I want. I can control and assign the number of elements, and to most appropriate to resolve the flow in this situation, and element sizing in the radial direction, in the axial direction, in the circumferential direction. Okay, so the resultant mesh, in addition to sizing, and assign several name selections to apply boundary condition that you will see in the calculation. So the resultant mesh, okay, if I zoom in here, by using the sweep method, right, I can generate a very nice all-hex mesh for all three parts, right? In this case, I specify 10 elements in the gap, which is sufficient. If you can do 20 easily, and 50 in the axial direction, all right? And so because this is a multi-body part, so once Workbench start meshing sweep mesh, the first part, and then you do the second part and the third part, and it generates a flow-through mesh on these connecting surfaces, right? So it becomes a flow-through mesh right here on this section, and right here on the rectangular, it's connecting to the cylindrical surface. So Workbench does give you this advantage, right? And so the advantage using flow-through mesh is now you have a one-to-one matching on these sections, and that is important, and we'll talk about that in a little bit when we build this model. So once this is done, because I can control the number of elements in the axial direction and the radial direction well, right? So I don't run into the excessive element count issue like what we have with the tetrahedron or prism, tetrahedron plus prism method. The total element count right here, you can see here the number of elements, 145,000. That is a reduction from 1.26 million, right? Almost an order of magnitude less, right? And this will help you tremendously, reducing your CPU time, as well as improve your solution accuracy, because there's less elements, and the hex meshes are less diffusive, and provides more accurate result in the flow gap and so forth. Right. So once we have the flow through mesh, the next thing is we're going to take it to the preprocessor CFX pre or Fluent interface to see what they're like and how we handle that. Now we have 3 flow volume, keep in mind, instead of just 1 big flow volume. So if we bring it CFX pre-surfaces, okay, that's the flow volume, 3 flow volume and the flow-through mesh that you can see here. In here, I'd assign the boundaries for the surfaces, right? That would be the end, the 2 ends, that's the inner cylinder, okay? And this is the outer cylinder. Did you notice one thing? If you notice that in CFX, if I don't assign an external surface, it would be designated as a default boundary, which means it will be treated as a wall, right? In this case, because of the flow-through mesh, CFX pre can identify the contact region. So in those regions, like this surface and that one, these are the 3 flow volume coming to contact. And because of flow-through mesh and these 3 volumes in a single part, CFX pre would treat those as internal nodes So there's no additional specification that is required for this situation. So that's one big advantage. If you can create a single part with multi-bodies, and you can take advantage of this feature, and you just have you don't need there's no additional concern or boundary that you need to specify, and you'll be treated as the internal volume, internal element. Similarly, if you look at Fluent, now we use this is the project page that I use. We look at the mesh, and we generate a CFX mesh, CFX pre. Then we look at the Fluent, use the same mesh, look at Fluent interface, and we take this into Fluent, right? And you notice that in the boundary zones, we do have the name selections that we specify, N1, N2, and showed up. These are the boundary surfaces. And in a similar way, because of the contacts are detected, automatically because of the flow-through mesh and multi-body parts multi-bodies in a single part. Fluent can also identify the surfaces, that the three volumes come into contact as the internal elements. Again, Fluent will take that as the internal nodes and elements, and you do not need to do something additional for these surfaces that you can see here. There's no wall boundary right here on this surface or on these two edges right here, right? Similar to the CFX. So with this in mind, so if you can decompose the flow domain into a single part with multi-bodies, and the workbench is able to mesh it to give you flow-through mesh, that would be ideal. Okay, that would be ideal. Then you don't need to worry about these interfaces at all. Next, we're going to talk about situation. What if you can't? What if the geometry is more complex than you think? Then you cannot do this. Okay, and that would be the last situation. Right? And in this case, instead of one single part with multi-bodies, now I have three separate parts. Okay, they don't belong to the same part, and there are three separate volumes. Right? What are you going to do with this situation? So in terms of meshing, now let's look at what the mesh look like. Right? And all three parts, again, they are sweepable. Right? I did the best I could to match the element count by specifying, a sweep method and element sizing in the circumferential direction, in the axial direction, and also in the gap in this cutout section, and just to match roughly the same element size for the rest of the domain, right? And all three volumes, I can use sweep method. That's a sweep method for the cutout, and that's a sweep method for the rectangular section on top of the cylinder, right? In addition to the boundary surface that I selected, similar to what we did previously with N1, N2, and in-wall and out-wall, in this case, I created 6 more, which are the 6 surfaces that these 3 parts come into contact. So each contact surface has 2 sides. So I name them interface 1, 2, 3, 4, 5, 6. Okay. So what the mesh looks like, because of the sweepable part, I can still generate sweep mesh, and I specify 10 elements across the radial gap, and match the element sizing as best as I can in the cutout section, and as well as in the rectangular section. And you can see clearly because they are not connected. I mean, they are connected, but they don't belong to the single part. So we don't have exactly a flow-through mesh, right? So these elements the element size are mismatched, right? So given that in mind, so this gives the idea. So now we have this situation. We need to do something different now to bring the flow volumes together in CFX Pre and Fluent. So the overall element count. Element is still very good. And remember, from the previous case, we have 145,000. In this case, we have 163,000. They both are, a significant number reduction from the default tetrahedron plus prism mesh. That would be 1.26 million, and we're looking at 95% reduction in element count, right, to resolve the same problem. So now we have the mesh in this situation, right? What would CFX and Fluent respond to this mesh? First, look at CFX. When we bring the 3 parts into CFX, CFX can identify interface by default. So without doing anything, you notice because the elements are not matched exactly on the 3 surfaces, so CFX generates a default fluid interface, okay? And it highlights these surfaces that these 3 parts come into contact. And for an interface, there's a side 1 and there's side 2. Okay, it generates by default, okay? And that's because CFX can detect the context, and we're fortunate in this case. What if it doesn't, right? And don't worry about that. Say, let's delete this for a second, right? What if it comes in and CFX does not recognize, the contact surfaces? Don't worry about it. You can generate it manually using domain interface features. So I'm generating a domain interface 1, right? And that would be the default domain. I'm identifying interface 1, and that would be matched up with interface 2, INTF2, and apply that. And you see that would be the first interface is generated. And we can do the same thing for the second one. That would be 3 matched up with 4. Okay, that would be that side. Sorry, this one. That would be 3 matched up with 5. Okay, so that's on the same surface. And then we can do with the third one. So that gives us the capability to put these domains together for these interfaces, right? So if you see CFX does not generate this interface for you automatically, and you can put them together manually. Now, what about Fluent? If we go to Fluent, right, we bring the geometry in, right, and we have all these sections, N1, N2, these are the boundary conditions, right? And we see these surfaces, they all come in. If we, let's display these sections, okay, not N1, okay. So do see these surfaces, INTF 1 through 6, are here, okay. So what are we going to do with that, right? Because now we need to do something different. They come in as a default wall boundary condition. So we have to switch the boundary condition from wall and to a mesh interface, okay, for INTF 1, and we'll do that for INTF 2 as well, to an interface, okay, and similarly for 3, 4, 5, 6. So now check these 6 surfaces, they all become interface now. So once they are defined as an interface, then you see the mesh interfaces feature, is now available. And we will create, using this function, to create the interface 1 mesh interface 1. Then I'm going to connect 1 to 2, right? And say create, just like that. And I have one interface. I can create a second one and connect the INT3 to 4, for example, and create a second one. And then the third interface, that would be 5 and 6 for the two sides. So based on the surface definition, the non-matching elements, that we created 3 mesh interfaces in Fluent. So by doing that, the numerical fluxes will be interpolated across the interface. Same thing, same methodology will be used in CFX domain interface as well. And because there's no one-to-one matching, so the solver will preserve the total quantities while interpolating them across the interface, to preserve numerical accuracy. So by doing this, we put the flow domain together, right? And we use a very efficient meshing method to reduce a large element count, from tetrahedron prism combination to a very effective, hex mesh, resolve the quantity we'd like to see in the radial gap and the axial direction also in the interface sections. Okay. So to summarize what we talked about today, let's go back to the PowerPoint slides. If we mesh a complex flow volume directly, and sometimes can be problematic and time-consuming, and we probably end up with large element count, and that's a result of isotropic tetrahedron elements fitting into very tight gaps. So it could be easier to look at, is there any potential, any possibility to divide the flow domain into several parts and take advantage of the very versatile workbench meshing method, apply the most suitable meshing method to each part. And by doing so, we can reduce the element count potentially by an order of magnitude. I mean, large reduction, or large amount of reduction. And directly related to this is reduce the CPU time, by almost an order of magnitude, which helps a lot. And this is important when you have a very large problem or you're doing an unsteady analysis. For example, if you have a long unsteady analysis run and you really don't want to use, excessive element count, use excessive elements that is not necessary. And that will help you, with your throughputs and get your calculation done more efficiently, okay? So once you have all these parts meshed, you can bring this together and stitch those flow volumes or integrated flow volumes together in CFX Pre using domain interface, or in Fluent, use mesh interface features. And the accuracy will be preserved by interpolating numerical fluxes across the interfaces and provide you with a good solution. The only suggestion is, if you do have this situation, you do not want to use the element size on the interfaces that are very different. So for example, the element size on one side is 10 times larger than the other side. And even you can connect them through interface functions, but you can imagine through numerical interpolation of the flow solutions, there will be some accuracy that is lost in the interpolation process. So, it would be ideal to have a flow-through mesh, obviously, but if you can't, try to create the interface mesh, with roughly the same size, and then use the interface functions, domain interface or mesh interface functions to integrate them together to help you with the analysis, or unsteady analysis or large problems with very large